Thanks, Philip, for the introduction. So yeah, I'm Tomas Teijeiro. I'm working in the Embedded Systems Laboratory at the EPFL in Switzerland. And we work mainly on energy-efficient algorithms and systems for long-term online seizure detection. I have to admit that sometimes it's a bit frustrating to say that I work on seizure detection because a common question is, okay, but that should be easy, right? The challenging part is prediction. And indeed, if somebody from outside the field takes a look at the most cited seizure detection review out there, which is from 2012, he can see or she can see that more than 15 years ago, we can check that almost every possible feature extraction and classification method approach was tested, and that the accuracy was almost perfect in all cases. So I think we are done. No need for anything else. But what are we doing here today? Well, is seizure detection so easy or not? Let me show you two results with two different types of signals. So first with EEG. This is an experiment in which we tried to build a general model for seizure detection. So we trained with 800 patients, and then we tested with 200 patients. And here in this figure, each row corresponds to a different patient. And for all of them, the seizure started at minute 2. So we can see that actually the network is quite proficient at recognizing the ictal segments. Indeed, the F1 score was 0.87. And there was nothing special with this network. It was a general model, and everything was plain machine learning. On the other hand, we can see that from ECG, if we see the distribution of a common feature extracted from the heart rate variability, the cardiac sympathetic index, we can see that the distribution during ictal and ictal is actually quite different. So if you are a machine learning practitioner and you find a couple of features like this that are not correlated, basically you are done. However, there is a trick in this picture. The normalization was done independently for interictal and ictal. What happens if we do a common normalization of the distribution? Well, where is the ictal? We need to do a lot of zoom, and then we can find that for any value out of the range of the distribution, from a probabilistic perspective, we should say that always it is interictal. I mean, there is no point in which ictal is more prevalent than interictal. And indeed, this is the main issue with seizure detection. It is not difficult from a machine learning perspective, but the class imbalance is the real challenge. So this is something that was already discussed in other sessions. But for example, if we have two seizure detectors, A and B, with this performance number, which one will you select? Of course, from a pure data analysis perspective, the first one is objectively better. However, if we consider a patient that, for example, has 1 seizure per week on average, then the method A will give a false alarm every 50 minutes. And this is completely unacceptable from a point of view of a user. So this is the importance of metrics. If we take a look at the positive predictive value, we can see that where is the real difference. So seeing this, we have to point out that from our perspective, from continuous long-term monitoring, specificity or different measures of specificity are the real key in seizure detection. And basically anything below 100%, as Philip said before, is not acceptable. So how do we deal with this huge data imbalance? If we take a look at the available data sets, the ictal duration ranges from 0.1% to 0.3% in common data sets. And maybe this is still too much for realistic scenarios. Maybe the real distribution is still lower than this. And seizure levels are very difficult to get, and particularly the end of the seizures. We all know that. The classical solutions from machine learning to data imbalance which basically are balancing the data via undersampling or oversampling, they simply don't work. If we do ictal oversampling, this usually leads to extremely overfitted ictal methods that don't generalize well. And if we do interictal undersampling, it is really challenging to get all possible representative patterns of interictal activity. So how we can get the most of all the data we have and at the same time produce good quality models? So our approach is to use two different models. One is a strong personalized interictal model, and the other is a weak general ictal model. So for the interictal model, we can use a lot of data. There is a lot of interictal data. That's not a problem. But then, since we need to model a single class, is just modeling the interictal, we need to build a model that is called single class, or an anomaly detection model. For this, we use the iForest algorithm, isolation forest. The basis of this algorithm is exactly the same as the random forest. And this algorithm gives a score to each observation in which we measure how difficult it is to isolate each data point in the data set. So basically, we have a bunch of decision trees, and each decision tree is able to isolate every point by taking a number of decisions, a number of rules. If we need a lot of rules to isolate a point, that means that it's not very distinguishable for the others, so it's not an anomaly. And if it is easy to isolate it, it is an anomaly. So basically, from this model, we have a score that says how interictal or not interictal is every point. And this score will be used to build our general ictal model. That has to be built with very few samples. And what we do is to set a threshold from the scores that are obtained from the models of all the other patients. So we have n patients. From the n-1 other patients, we see the distribution of the scores during the seizures. And we select a threshold based on, for example, the number of false positives per day that we are able to admit. The good point of this is that this threshold can be personalized very easily. It is a very simple model. It's just a threshold. So for example, if we observe a seizure from a patient that has not been detected, we will be able to adapt our score to be able to at least this exact same type of seizure to be detected in the future. But also, if we want to do a long-term seizure detection, we need to make efficient models. And for ensuring the efficiency, the energy efficiency of the algorithms, our approach is based on the concept of self-awareness. In self-awareness, you have a system, and then you include mechanism to be able to observe in real time what is the performance of the system. From this observation, you can analyze the performance a long time and modify the behavior of the system. So you are able to adapt a long time how the system is performing. So self-awareness basically adds control units to monitor the performance, adapt to changes, and improve autonomously. Here we can see the workflow of our self-aware seizure detection system. This one is based exclusively on ECG signal. And then we can see that basically what we have is different models, and each of these models have a different complexity, and at the same time a different energy footprint. So more complex models have lower errors, but also consume more energy, and simpler models have a slightly higher error, but consume less energy. So while you are performing the detection, you are starting, it's like a tree. You start with the simpler models. If the confidence of this model is enough, then you give the result. If it is not enough, you go to a more complex model. And you can do this in a hierarchical way. The complexity is based on basically on the number of features you need for doing the classification. And here in this table, we can see the results of this approach. So in the first column, we have the different levels of self-awareness. The second column is the threshold we put on the confidence we require to use a more simple or a more complex model. Then the third column is what is called responders in the literature. That is, a patient is considered a responder if more than 2/3 of their seizures are detected. And the total number of patients in the datasets were 43, by the way. Then we have the false alarm rate per day of the responders and the sensitivity of the responders, and the general false alarm rate and sensitivity. And the last column is the complexity of each of the models. So on one extreme, we can get more or less half of the patients as responders with a false alarm rate around 3 per day, and the sensitivity, the total sensitivity is 59.5. On the other extreme, we can get 32 responders, but the false alarm rate is 1 per hour. And the total sensitivity is 77.9. And then, modifying the threshold of the confidence we require, we can get different values of responders, sensitivity, and false alarm rates. So, and the complexity can be reduced up to a 70%, compare the simplest one with the more complex one. However, we can see this false alarm rate is still too high for practical implementation. Even the lowest one, that is 3 per day, can be considered too much. So what we did was a false positive analysis, which is very useful in these cases. And we observed that most false positives occur in segments with high noise and artifacts in which the heartbeat detection fails. For example, here we can see in blue, we have the ECG. In green, we have the different heartbeats marked by the algorithm. And we can see that there are areas in which this detection completely fails. And this happened for most of the false positives. But we also observed that during seizures, there were many heartbeat misdetections. So this effect happened also during seizures. On the lower part, we have a seizure in which the marked areas correspond also to areas in which the detection didn't work well, and they are very noisy. So in the end, what we are actually detecting, what is our system detecting? So we implemented a quite efficient method for improving the heartbeat detection based on the Kalman filter. And the objective of this was to improve the reliability of the RR series and of the HRB features. But the detection dropped after we implemented this. And here, these plots can be a bit complex, but let me explain you. The X and Y axis are the two more relevant features. In blue, we can see the distribution of the interictal, and in color, it is the distribution of these features during the seizures. So the left part is before implementing the filter, and the right part of each plot is after implementing the filter. So we can see, for example, in the top left, that during seizures, the values are much outside on the interictal. However, after we improved the quality of the HRV, the separability dropped dramatically. So actually, what our system was detecting was basically periods of tachycardia correlated with high noise in the signal. But this, for this data set, was good enough for providing a detection of the seizures, but we know that this is not robust. In general, you cannot rely on just tachycardia and noise for detecting seizures. Otherwise, probably I will be having a seizure right now. So indeed, we did a statistical test to compare, okay, let's measure the errors in the detection during seizures and during non-seizures and see if they are statistically comparable. Well, only one patient had a p-value over 0.05. All the others were lower, which means that the distribution of errors during seizures and during non-seizures is different, clearly. So what is the solution to this? How we can improve the robustness of this system? Well, usually the answer is going multimodal. So in the picture, we can see a typical architecture of the next generation of wearable body sensor networks, in which We have different sensors that provide different types of information that can complement the others when there is some noise. For example, EEG that can be embedded on glasses, the PPG or EDA that can be in a wrist device. All this can be coordinated by a smartphone that provides data fusion at a higher level. And even we can use cloud models that make a general model for many patients to complement the results. However, this strategy has some drawbacks. It is rather inconvenient for the user to add more and more wearable devices. So you have more devices to wear, more devices to recharge, etc. Then it is difficult to synchronize and processing all the data, and is more prone to errors. So it is possible to get the best of both worlds. I mean, having the robustness of a multimodal system, but using only one type of signal? Well, the answer is no, but almost. So for this, we tried a method based on the concept of knowledge distillation, in which we use different models for different stages. So we start with a robust multimodal model that is built using EEG plus ECG, and we call this model a teacher. So we train this model with the multimodal data, so the performance should be better. And then we have a simpler model that we call the student that is trained only using the ECG. And this model is trained by using as labels the output of the teacher model. But what is the difference with respect to normal training of a model? Well, let me show you an example of a real seizure in which we can see 4 channels. The seizure starts at second 20 and finishes, well, I'll show you now because this is the label that we have in the data set. Let's call this the hard label. So the seizure starts at second 20 and finishes at second 75. So all this is a seizure. So any machine learning model that you try to fit with this label will try to give a positive answer to all this segment. It is the same the first second and the second and the third. However, if we take the output of the teacher model, this will be, and let's call this the soft labels. So you can see that these labels from the teacher are much more expressive than the original labels. Because, for example, after 5 to 10 seconds, there was a clear mistake, error, a noise in the signal that becomes plain. And the teacher says, okay, don't focus on this. This is not important for a seizure. So this allows the student to concentrate on areas with clear ictal or interictal patterns. And it is very interesting that these soft labels can be interpreted and validated by humans. And we cannot ask the doctors to do this kind of labeling. It is enough to say, okay, label of the seizures, but you cannot say second by second, yeah, this is clearly a seizure, it is not clearly a seizure. So this is extremely useful for the training. And we can see it in the results. In the left part, we have a system trained exclusively the ECG and the original labels. In the middle, we have the teacher model, which uses the multimodal and the original labels. You can see that the F1 score increased almost 10 points. And in the rightmost part, we have the student model that was trained using exactly the same data as the first model, but using the labels from the teacher, rather the original labels. And you can see the performance drop is negligible. So it is clearly an improvement of the training process. And now let me finish by talking you a bit about one of our latest lines of work. We think is probably the most promising one. It is what we aim to build is what we call the epilepsy digital twin. And the objective here is pushing the notion of personalization to the limit. So the objective is to build for each specific person a set of a personal model that is like a fingerprint from the different signals we are acquiring from it, and to be able to detect specifically the intra-patient reproducibility we have observed, and also that was discussed before. So to see if this is feasible or not, we performed, well, first of all, sorry, this digital twin, our vision is to embody it in wearable devices. For example, a pair of glasses that will capture the EEG and accelerometer, and a smartwatch that could complement this data with also cardiovascular data. And in order to validate if this approach will be more or less feasible, we perform a experimental validation that was mentioned before by Philippe, in which we use two public databases, the CHB MIT and the Epilepsy. This makes a total of 54 patients with more than 5,500 hours of continuous EEG monitoring. And for each patient, what we did is to visualize two randomly chosen seizures from 30 seconds before the beginning up to 1 minute after the beginning. And we try to identify morphological patterns that seem to be consistent among this pair of seizures. This was done basically, the motivation for selecting a pattern was basically the morphological similarity. It was not based on a physiological interpretation. And these patterns should have at most 2 channels. Well, we limit it to just 2 channels. And we allow to have up to 3 patterns per patient in order to account for different seizure types. So once we selected a pattern for a patient, what we do is to match this pattern with the whole duration of all the data we had for that patient that was on scene. For example, here between each pair of bars, it is 1 hour. And we use a dynamic time warping metric to do the matching. So in this picture, you can see the green bars correspond to the seizure, and the blue line is the distance metric. And then we see, okay, what is the optimum threshold that allows us to detect as many seizures as possible without any false positive? This was one of the constraints we imposed. We accepted no false positives in the whole duration of the patient. And these are the results that were shown before for the 2 databases. As an overall number, we could detect the 82% of the seizures, 91% in the CHB MIT, which was indeed easier, and 75% in epilepsy, and no false positives, as I said before. The median detection delay was 17 seconds, with 85% of the seizures detected in less than 40 seconds. And this is very interesting. 28 patients required just 1 pattern, and 19 required 2 patterns, while 3 patterns was only necessary for 4 of the patients. So in general, it seems that 2 patterns should be enough for most of the patients. So just to conclude the talk, I would say that discriminating ictal and icterintal segments is not so difficult. From a machine learning perspective, this is not the difficult where it is. The main challenge is the data imbalance in real monitoring scenarios. This is what we should deal in our studies and include in our data capture and data plans. The key strategy to reduce the false positive rate in long-term monitoring are personalized models. This was already said today, so I think we most agree on that. Multimodal approaches are more robust in day-to-day monitoring, and they can be exploited even if they are only used on training stage. You don't need multimodal always, but still multimodality gives robustness. And finally, the development of the epilepsy digital twins seems feasible based on the concept of the personalized seizure signature. And that's all. Thank you very much for your attention, and if you have any questions.
Thank you for your presentation. I just have a question. On the one side, there is the hope for some generic algorithms, but that is not very promising. On the other side, you have the highly individualized, personalized approach. Don't you think there is an in-between, that we might see some patterns that in the end we need only 3 or 4 algorithms because there may be categories of patients, and that it doesn't need to be so extremely personalized?
Yes, I think so. And indeed, one of the approaches we try to follow as well is to try to build these weak general models that can be then adjusted for each specific patient. And probably if we are able to cluster the patients in different groups, this will be much easier. Because now, yeah, there is also in the data sets we have, there is the general concept of seizure as it is, and all are treated the same. But this is clearly not the best approach, because there are different types that are clearly more consistent between them. And I think that will be the way to go.
Hi, Ben Valandrisa from Byteflies. Very interesting talk. I have a question that I was actually thinking about during the presentation from Professor Yvlan, but I think based on what you've presented here, you might be able to answer it as well. So when we're talking about multimodal, and especially fusing multimodal data sets in order to increase performance, and then as Professor Yvlan demonstrated with that one paper, that can actually backfire and it can reduce your performance again. So with a lot of these approaches, especially when they use neural nets, you have the potential benefit that it's an end-to-end system, that you can train it based on all your input data and whatever output you're trying to generate. But with that approach, we're also throwing out decades of domain knowledge of how these different signals relate to each other and what we already know. So what's your opinion on making sure that we don't just simply discard all that knowledge and try to incorporate it into maybe a different way of working that is not really focusing on this end-to-end approach?
Okay, so first of all, my personal opinion is I hate neural networks. So that's the, so now you can imagine. I'm absolutely for, and we have several works that prove this in other problems, that mixed models that integrate expert knowledge have a fundamental advantage over purely data-driven algorithms. There's no way with the data we have now, or with the volumes of data we have now, that a pure data-driven algorithm can reach the point of a model that includes some even very simple constraints about, okay, what is the minimum time that can happen between these two events? Just this minimum amount of expert knowledge increases a lot the robustness of a solution. So this is clearly the way, on my opinion, of course, but yeah.
So now that you revealed where your heart lies, let me ask you this, the following question. You stated that we cannot accept anything below a specificity of 100%. Okay, but you didn't really give the context. You spoke a lot about false alarm, which I agree are a big issue for the patients themselves, but if you include the expert in the loop, then actually a lower specificity is absolutely acceptable, and an expert could easily review up to 20 samples per patient per day. So I think this is also the first step we should aim for, is that we still have the expert in the loop who corrects and enrich the quality of the detections.
Yes, absolutely. As Mark said, it depends a lot on the use case. I was more thinking about, long-term monitoring and giving feedback to the patient directly. But of course, if it is for helping out annotating large volumes of data, that's totally acceptable. And indeed, maybe it's better to increase the sensitivity and give, okay, I will give you 3 more false positives to check, but you will disregard it in 10 seconds. So absolutely. All this, there are no absolute claims in this side, but you're totally right.
Maybe just, Maxime, to add a few words to your comment, and I agree with you. First of all, of course, some level of false alarm is acceptable in general, but I think that when we test a system in the EMU, we need to have very stringent criteria, because in the real world, it will be much worse than in the EMU. So that's number one. Number two, indeed, if tomorrow we have systems that can really learn from the patient that wear them, then false alarm during a training phase will be indeed useful to train the system, actually. And so we can imagine that the patient will know, well, for the first few weeks, you will have false alarm. In the same way, for the first few days of your drug, you will have some side effect, but they will be weaning off, and that's part of the game. So indeed, that's definitely something we can envision.
Hi, thank you for your presentation. I have a question about noise and noisy data. Whether you think that certain noisy patterns may be quite specific to seizures and we can learn from them. I'm thinking about the obvious examples of tonic-clonic seizures, but also certain patterns, certain chewing patterns that are more specific to oral automatisms. So
yeah, absolutely. Indeed, one of the tests we did with this same experiment was, okay, with the HRV features, this is what we can get. So let's avoid the noisy segments, and then let's try to distinguish the noisy segments directly. And for some patients, it was quite separable, the noise from seizures than other types of noise that happen. So this is really a way to follow. I mean, we need to make the most of everything that happens that can be distinguished, but in general, noise is not very specific, so we need to be careful with it. But if it gives information, yeah. It's a very good reflection, yeah.
One remark also to the use of CNNs. I think I totally agree that one of the advantages that we may have is probably that algorithms can improve over time. And I think the data that we have, which are highly valid in terms of real seizure detections also in long term, are very rare, and I think it's probably up to us to find ways to collaborate and form databases which are then the basis for improving these algorithms for specific patterns and for specific seizure types associated with specific patterns. And I think that the neural networks will probably perform a lot better if we have the option to really found such databases and such international collaborations than working on relatively limited data sets as each of us can provide that.
Yeah, indeed. And I think it's very important to make sure that we are trying to include in those databases the effects that we don't want the automatic algorithms focusing. For example, we have observed that our model what learns is tachycardia plus noise because it is the most remarkable feature that happens during seizures. So if we are able to include also in the databases tachycardia, induces tachycardias that are not related to seizures, this will improve the thing. So otherwise, the algorithms will always go for the easiest thing.
You go to the gym and you have a problem. So it is, you have to adapt it to real life conditions.
No, but that's precisely what I'm saying.
We need really large data sets, and joining these data sets and marking them appropriately, I think, because all of the data that we get in our monitoring is certainly biased to some degree as well.
Yeah, and probably, 7-10 days of continuous monitoring is not enough for giving a good representation of all the life of the patient. Absolutely.
During the knowledge, thanks for the presentation. During the knowledge distillation process, have you also looked at which features are most specifically resulting in high specificity rates for your case? Maybe you can in the future narrow down to your model to a more simpler model which will still have very high rate. And second thing is that based on the earlier presentation, if I'm correct, we also learned that sensitivity rate is very important. It is what the caregiver wants. So maybe what are your comments in that? And
regarding, well, let me start with the first one. What we observe is that basically what the models fit most is on ECG is the heart rate, clearly, and on EEG is the amplitude, which is clearly an important feature, but we know that amplitude is very prone to noise. I mean, noise affects amplitude on top of the other. That's why we have to be very careful and have enough representative data of different noise patterns and things that happen to avoid that the network or the model collapses to just learning that. And then for the sensitivity, what was?
I asked that based on the earlier presentation, we also learned the sensitivity rate is very important, and it is what it is important for caregivers also. So your comments on that for improving that as well.
Well, in the end, there is always a balance, and the way we have observed it is more efficient is the personalization, in order to improve both things at the same time. Otherwise, it's very difficult to have a general model that when you increase the sensitivity, the false alarm rate increases as well. This has been observed.